Hello everyone and welcome to lecture. Today's lecture will be about multivariable functions and critical points. So multivariable functions and the critical points of multivariable functions. And this is going to be related to the idea of single variable multivariable functions. So the idea here is we're going to start off by reviewing the definition of a critical point for a single variable function and see how this almost directly generalizes to multivariable functions. So recall from 1D calculus, right, in 1D, for a given function of x, say we have y is some function of x. We can have two main types of critical points. For instance, this function might come up to some maximum here and hit a local minimum right here. Maybe there's an inflection point of the function. So it comes up, goes down, there's a point where concavity changes, and maybe you have some discontinuities, a cusp point right here in the derivative. This is a nice picture, say, of a possible example function of x. And we'll just kind of consider the interval, say, from a, go from right here, to b, right here. So on this interval from a to b, this function has, looks like it has 4 critical points. x1, x2, x3, then x4 right here. And these are all critical points of the function because they're all points where either one of two things is true. At each one of these points on this interval, we'll say a point x star is a critical point of a function f of x in 1D if either the derivative at x star, the rate of change of the function f at x star, is equal to 0, or the derivative at x star does not exist. which we'll abbreviate as DNE for short. So here you can see that x1, x2, and x3 are all critical points of type 1. Is the slope at x1, the slope of the tangent line at x2, and the slope of the tangent line at x3. Each one of these has 0 for the rate of change. So each one of these, x1, x2, and x3, are critical points of type 1. Whereas x4 is a critical point of type 2. Or a critical point, it's a critical point x4 because the derivative just does not exist there. The slope does not exist at that point. It's a cusp point, similar to the absolute value function at the origin. And you see that each one of these types of critical points are important to deal with. Both of these types of critical points are important to deal with because in general, both of these types of critical points are points where the function could possibly attain a local max or min. And when it comes to, say, optimization, so optimizing an output of a function or optimizing something, you have to be very, very careful about finding all of the critical points of any given function. So we want to see how to take this idea and directly generalize it to multivariable functions. The main question that we want to ask ourselves is how to take this or generalize this classification to multivariable functions. And the idea is that we have almost a direct generalization for multivariable functions. So what we'll do is I'll write the general classification, and then also we're going to focus on the 2D case. But turns out that this is directly possible to generalize to multivariable functions. For a multivariable function, function f of r, depending on any number of variables, we say that a critical point which we'll denote as r star. It's a vector now because the domain of the multivariable function is in multidimensional space. The critical point r star, I guess we say r star is a critical point if one of the following is true. And the first case is very similar to the first case in the 1D case. It's that the derivative of the function or in some sense, the derivative of a function is the linear approximation of the function, or the linear approximation of the function, or linearization. This is directly dependent on the gradient vector. So we say that a critical point is a critical point if the gradient vector of the function at the point r star is it's exactly equal to the zero vector. Or the gradient of the function just flat out does not exist. This is our direct generalization of the idea of a critical point from 1D into ND. Now for 2 dimensions, or for a function of 2 variables, this becomes straightforward in terms of the partial derivatives. What this means is that a critical point for a 2 variable function, or in 2D, if the gradient is equal to the zero vector, then both partial derivatives have to be equal to 0. So the x partial derivative at r star has to be 0, and the y partial derivative of f at r star has to be equal to 0. And likewise, the other type of critical point in 2D for a function is if the gradient vector does not exist, which means that either the x partial derivative at r star does not exist, or the y partial derivative at r star does not exist. Instead of that and symbol, I'll write and. So the idea is that these 2 conditions for a definition of a critical point can be applied to functions of 3 variables or 4 variables as well. But it turns out, when we get to classification of critical points, as a local max or a local min, the idea of doing it in 2D is going to be easiest. We can extend it. It's possible to extend to functions of more than 2 variables, but we're going to stick with functions of 2 variables for this course and for this lecture. So the idea is that the method of computing critical points for a function, just like in the single variable case, ends up being a matter of solving a system or solving equations that guarantee that this is true at a given point. So, like, either guarantee that the gradient is equal to 0, or if the partial derivative does not exist, then you'll have to show that one of the limits does not exist for one of the partial derivatives. A good example is the roof function. At certain points on the roof or the cusp, or if you have like a cusp, say, anytime you have a cusp on your surface. So for instance, let's say you have a surface or a function of 2 variables with a surface that sort of comes to some cusp or some point at it right here. This would be a point. As an example of a critical point of this function, because the partial derivatives don't exist at that cusp. In general, at critical points of either type, you expect to have local maximums, local minimums, and what are called saddle points, which are similar to inflection points. But this is a general thing that we expect for multivariable functions. So classification of these types of points is going to be very, very important as we move along. So I've made a helpful kind of image here to really kind of help us visualize exactly these 2 different types of critical points. For critical points of type 1, we have here, right, we can have either a local min, a local max, or a saddle point. Now, there are many different types of saddles. We'll see a different type of saddle in one of the examples I'll talk about later on in the lecture. But you see very clearly that at a local min, the tangent plane is horizontal on the graph of the function. Right, so this is just a plot of what the graph of a function of two variables looks like at a local minimum, and you see very clearly that the x partial and the y partial are both 0 here. Same thing at a local maximum and also at a saddle point. So just because you have a critical point doesn't necessarily mean that you have a local min or a local max. You would also have a saddle, and this is very, very important. It's going to be super important in optimization. The other type of critical points, which are types of critical points where the derivative does not exist, are also very important. You can see here, clearly I've just shown in this picture an example of two different types of local maximums that could occur at cusp points, or points where the derivative does not exist. This first example is like a pyramid type function, where you have this cusp here, which is a local maximum, and then similar here, this is like a smooth function, but still this function at this point is not differentiable. It's continuous but not differentiable, and there's no way of defining the tangent plane that uniquely approximates the function. So the idea here is that when solving for the critical points, we have to always have to consider both types of critical points, and doing so is very important when trying to find the global maximum of a function on some region. So it's a nice, very, very nice kind of diagram showing what we expect. Well, let's go through and see this for an example. And for this example, we'll stick with the function from example 1 of the previous lecture, which is the function f of xy is equal to x times y times e to the negative x squared plus y squared. Calculated that the partial derivatives of this function were df dx, which was y times 1 minus 2 x squared times e to the negative x squared plus y squared, and partial f partial y, which was x times 1 minus 2y squared, e to the negative x squared plus y squared. So in order to solve for the critical points, we have to ask ourselves either how many critical points of type 1 are there, how many critical points of type 2 are there. Turns out for this function there are no critical points of type 2. And that's because the exponential function is an infinitely continuous function. It's a nice, smooth function. And the function x squared plus y squared is also continuous. So therefore, e to the negative x squared plus y squared is a very nice, smooth, continuous function. And same thing with the function x times y. So because of that, this multiplication, it's like a multiplication and a composition, is also a very nice, smooth function with infinitely many derivatives. So there are no critical points of type 2, but there definitely are probably going to be critical points of type 1. So we need to figure out how to solve for the critical points of type 1. And in general, this can be done by taking the partial derivatives, setting them equal to 0, and then solving the resulting system of equations that you get. So in this case, we have to set the x partial derivative, which is y times 1 minus 2x squared times e to the negative x squared plus y squared. This has to be equal to 0 at a critical point of type 1. And we also have to set the y partial derivative equal to 0, which amounts to x times 1 minus 2y squared times e to the negative x squared plus y squared equal to 0. So we have a system of two equations that we have to solve, and the solution of this system of two equations for two unknowns x and y, all of the different solutions of this system of equations will give us all of the different critical points for this function, the function we're interested in. Now, it's important to note here that this system is a nonlinear system. Just like for solving for critical points in 1D for one variable functions, you typically get a nonlinear equation that you have to solve for x, which means there are possibly many solutions for the critical point that you're solving for. You could potentially have infinitely many solutions for critical points. If you have like a sine or a cosine in there, you very often will have infinitely many possible values that you can solve for that satisfy the equations that are written down. So for this example right here, we got to figure out the easiest way of simplifying this system and trying to solve it. And the main way we're going to do that is that you want to remember that for any value of u, e to the u will always be strictly positive, will always be greater than 0. And therefore, because e to the u is never equal to 0, you can always divide by e to the u for any exponent u. And that's the first way we're going to rewrite this. If I divide equation 1 by this e to the negative equation 1, and we're also going to do this to equation 2 by e to the negative x squared plus y squared, this will give us the following. Give us two new equations. Call it equation 1 star and equation 2 star. Equation 1 star is going to be y times 1 minus 2x squared is equal to 0, and x times 1 minus 2y squared is equal to 0. And this system of equations is definitely simpler than the one we started with. And the reason that we can do this in simplification is that that e to the negative x squared plus y squared is always, no matter what x and y are, it'll always be positive. So it won't be 0, and therefore we can divide by it because it's non-zero. Now, if instead it were possible that it equaled 0, you would have to think of some other way of simplifying the system of equations. There'd be some other thing that you'd have to do to kind of simplify that system. But because of the fact that this is we can do this, we get a nice, much simpler system to solve. So the idea then is that we have this new system that we have to solve, and we have to look at and see, well, how can we satisfy this system? What values in x and y, with x and y, are going to give us solutions to this system? And the key thing to do almost always is to start with one of the equations and figure out what values of x and or y will satisfy one of the equations. So in this case, we'll probably start with equation 1 star, and then you can go through and see what that implies about the other equation, equation 2. So let's go through and do this right now. So for equation 1 star, right, this is satisfied if one of two things is true. If y is equal to 0, or if 1 minus 2x squared is equal to 0. If y is equal to 0, then equation 2 star becomes the equation x times 1 minus 0 is equal to 0, or the equation x is equal to 0. Which means that our first critical point is the point 0, 0. X equals 0, y equals 0. If 1 minus 2x squared is equal to 0, that means that 1 is equal to 2x squared, or x squared is equal to 1/2, or x is equal to plus or minus the square root of 1 over 2. Which actually give us two other critical points. Corresponding to x equals plus or minus 1 over the square root of 2. But this also gives us something else to think about, right? If x equals plus or minus 1 over the square root of 2, we have this is satisfied, so equation 1 star is satisfied, but x is not equal to 0. You have to also guarantee that equation 2 star is satisfied. In equation 2 star, if x is plus or minus the square root of 1 over 2, becomes the equation that plus or minus 1 over the square root of 2 times 1 minus 2y squared is equal to 0. And if we make some more room here so we can see this process out. In its entirety, so the only way of satisfying equation 2 when x is plus or minus 1 over the square root of 2 is having 1 minus 2y squared be equal to 0, which means that y squared is equal to 1/2, or y is also equal to plus or minus 1 over the square root of 2, or the square root of 1 over 2, or 1 over the square root of 2. So we have one critical point from this procedure, and this procedure has given us 4 critical points, a total of 4 critical points. Now I'll to simplify what I'm about to write down, we'll let L be equal to the value 1 over the square root of 2. But from this procedure, we have that the critical points are located at L, L, negative L, L, negative L, negative L, and L, negative L. Because what we've just shown is that any combination, right, of plus or minus L for x or for y gives us the value of a critical point. So x could be plus or minus L and y could be plus or minus L. Any combination of those two values will guarantee that this is 0 and this is 0, which satisfies our two equations. Therefore, these are the 4 critical points of our function. So we can visualize this, okay, what this is going to look like. Directly. We plot out our x-axis and our y-axis. We solve for the point x equals 0, y equals 0 is a critical point. The point 1 over the square root of 2, comma 1 over the square root of 2 is a critical point. The point negative 1 over the square root of 2, 1 over the square root of 2 is a critical point. The point negative 1 over the square root of 2, positive, or negative 1 over the square root of 2 is a critical point. And then lastly, the point negative or positive 1 over the square root of 2, negative 1 over the square root of 2 is a critical point. So this function, and the solution to that system of equation gives us 5 total critical points of this function. And if we do a visualization of this function, we can clearly see exactly what this looks like. So using my Python code, I plotted each one of these out, and you can see that what we've computed is exactly correct. So we'll look first at the 3-dimensional plot, which is the bottom plot here. You can see very clearly that if we kind of rotate this function around, we're seeing exactly those 5 critical points that we calculated before. And from the plot, you can see that 2 of these points are local maximums of our function. 2 of these points are local minimums of our function. And 1 of these points is exactly a saddle point. So the origin is what's called a saddle point of our function. And a little bit later on in the course, we'll talk about exactly how to classify the critical points for a function of 2 variables. We can get classification tests for functions of more than 2 variables, but the more variables you have, the more complicated in some sense these classification tests become. But it's still possible to derive general classification tests. But it's probably shown a little bit more clearly in the other plots. So you can see the 3-dimensional plot clearly is showing that we have a saddle point, and then 2 local maxes and 2 local mins. But if we consider either the density plot or the contour plot, right, we're also seeing exactly this. And it probably shows it a little bit more clear that the point plus L and minus L plus minus L are local maximums of our function, because the gradient vector is pointing in around each one of these points. The local minimums, negative L positive L, or positive L negative L, are their local minimums because the gradient vector is pointing away from each one of these points. And we also see that this saddle point, 0, 0, the gradient vector in certain areas is going into the saddle point, but in other areas is moving away from the saddle point. So what you're seeing here is actually, it's kind of like a generalization of the first derivative test from Calculus 1. So it's a generalization of the first derivative test from Calculus 1. And that's our first main idea that we can kind of see right here, is that in order to classify these critical points, we can do so with the first derivative using the gradient vector. If you look for points where the gradient vector is moving away in every region around the point, that's a local minimum. But if you look for and you find a point where the gradient vector is pointing in towards the point, for all points around the critical point, that's a local maximum. And a saddle point is when you have regions where the gradient vector is pointing into the point, but also you have other regions around the point where it's pointing away from the point. So this is just one more plot that I produce to kind of emphasize and verify the results that we just obtained. Here you can very clearly see the 5 critical points that we just calculated, along with the fact that 2 of them are local minimums, 2 of them are local maximums, and one of them, this middle one, is a saddle point. And if we change our view here, this is a contour plot. If we change our view to the graph view, we can kind of very clearly see why. For these 2 points, the gradient vectors are moving into the points, just like in the previous plots. For these 2 points right here, the gradient vectors are moving away from the 2 points. And for this middle point right here, we have regions where the gradient vectors are moving away and into this middle point right here, which clearly establishes that this is some sort of saddle point. But this is just another figure here that demonstrates this idea of critical points and verifies the calculations that we just did by hand, which clearly shows how powerful this method is. So let's consider one more example, just to kind of really bring home the point and make sure that we understand exactly what we've just discussed. So we'll consider the function 3y squared minus 2y cubed minus 3x squared plus 6 times x times y. So to solve for the critical points of this function, we have to solve for all of the points where the either any of these partial derivatives of this function do not exist, or any of the partial derivatives are all simultaneously equal to 0. Because it's a nice polynomial function, there are not going to be any points where the derivative does not exist. So there are no critical points of type 2. This is always something that you need to check, and is very important to check, because for more complicated functions, there could very well be cusp points, or points where the derivative does not exist. But for this example, there are no critical points of this type. So this leaves us with one and only one other option for critical points, and this is points where the gradient vector is equal to 0. For critical points of type 1. So in order to solve for these points, we have to go through and look at the partial derivatives. The x partial derivative of this function is going to be negative 6x plus 6y. And when we're solving for these critical points, we're solving for points where df dx will be 0, and simultaneously we need df dy to also be 0. And df dy is going to be 6y minus 6y squared plus 6x. So we'll call this first equation equation 1, and the second equation equation 2. And go through and see if we can solve this system. Just like before, this is a nonlinear system of two equations. We expect there to be a number of different possible solutions if there are any solutions. And sure enough, equation 1 is satisfied relatively easily. This is satisfied when y is equal to x. So this is the only possible way that we have of satisfying equation 1. Equation 2, on the other hand, is a little bit more complicated. So equation 2 will be satisfied if this 6 times y minus 6y squared plus 6x is equal to 0, and assuming that equation 1 is satisfied, so y equals x, we can substitute into equation 2 to get the equation 6 times x minus 6 times x squared plus 6 times x must be equal to 0. And this is something that needs to be solved then to simultaneously satisfy equation 1 and equation 2. This is the same thing as negative 6x squared plus 12x is equal to 0, or if we factor out 6x, it's 6x times negative x plus 2 is equal to 0, which has two solutions, solution corresponding to x equals 0 and a solution corresponding to x equals 2. And so putting this all together, we have that the critical points of this function these are the critical points of type 1. There are no critical points of type 2, as we mentioned earlier, are 0, 0, and 2, 2. Now, I want to emphasize, just like for before, by visualizing either a density plot or the level curve plot or gradient plot of this function, or even the graph of this function, we can quickly demonstrate, right, whether these points are going to be saddle points, local maxes or mins, or what the nature of these critical points are. Now, analytically speaking, we need to develop some more machinery before we can actually classify and definitively classify what types of critical points these points are. However, what I'm going to do now is run the Python code, and we're going to go through and I'll show exactly what types of critical points these are. And it's very, very apparent when viewing either a density plot or the graph plot of this function. So I just ran the Python code, and this right here is a visualization of this function. You see very clearly that the point 0, 0, which is one of the critical points that we calculated, is a saddle point of this function, because there are regions where the function is increasing as we approach the point, right? And it's also increasing as we move away from the point. Or as we move away from the point in these two directions, the function is decreasing. And if we move away from the this point right here in this direction or in this direction, the function is increasing. This is a type of saddle point. And the point 2, 2, this point right here, this is a local max of our function. Locally, the contours are surrounding this point right here. And as we move away from the point, the function is decreasing in every direction. So, we will be able to use our second derivative test to formally do this with the machinery developed in the next lecture. But this is just a good, nice kind of plot showing this right here. And if I kind of move to a 3D view, that we can see the surface plot of this function, the graph of this function. There's nothing special with this circle here. I just kind of did this boundary circle to indicate how the function is changing on a circular boundary. We can clearly see that at this point right here, 0, 0, the gradient field is moving away in this direction, and it's kind of hard to see here, but if I change the scale, you can see that the gradient field is also moving away in this direction as well. So the function is increasing in this direction, decreasing in this direction. Its gradient's decreasing in this direction, decreasing in this direction, and oops, sorry, it meant it's increasing in this direction right here. So this point is clearly a saddle point, and you see down here this gradient plot where as the function is increasing very steeply in this direction right here, the gradient's getting larger and larger. Same thing right here, the function is increasing in this direction right here, and it has a very big magnitude when we're in regions of very fast change of the function. Hence why the level curves of this function here are closer and closer and closer together. So this is a really nice picture demonstrating this idea and demonstrating the 2 points that we just found by hand are in fact the correct critical points of this function. So this is really neat. This picture also illustrates something that is going to be really, really important to us when forming our optimization procedure. Let's say we wanted to find the global maximum of this function on a circle, or on this drawn circle right here. Well, sure enough, potential maximums of the function, global maximums of the function, are going to be inside the domain at any and all interior critical points. So our procedure is going to be solved for all of the interior critical points to a domain. And then the second part of our procedure is going to be to look on the boundary, because this is a great example of a function that actually attains its global maximum, which is right here, and its global minimum for this domain right here on the boundary of the domain. So we always have to look inside the domain at interior critical points and on the boundary of the domain when we're finding the maximum value and the minimum value of a multivariable function, just like in 1D. Which is really, really important. But that's going to be the topic for the next lecture. And well, I'm going to leave it here and end the lecture right here. I hope you learned something and had a fantastic day. And I look forward to seeing you in the next lecture.